Let's discuss Rolle's theorem. I'm going to jump right into it. Rolle's theorem states, suppose that y is equal to f of x. It's continuous over the closed interval a to b, including the endpoints, and differentiable at every point on its interior. If f of a is equal to f of b, then there exists at least one number c in the interior a to b at which f prime of c is equal to 0. Alright, so let's walk through that and know by now that I like to illustrate things with pictures. So let's think about what the picture looks like. We have a continuous function on a closed interval a to b. We know that on those endpoints, the a and the b are equal to one another. F of a is equal to f of b. And we know it's continuous between those points. Okay. So if this is part of a larger if it wasn't on a closed interval, we can always kind of find a closed interval. This could be part of a larger function. But in particular, what we're looking at is the fact that these 2 points have the same value. So I don't necessarily care that they're endpoints. I can always form endpoints out of 2 closed points. I care about these 2 values being the same. They have the same y value at a and b. Well, the only way that that is true, that these 2 things have the same value and is continuous, is if it had to have turned around somewhere in the middle. We're never going to get the same values unless somewhere in here we would have a horizontal tangent line the function had to turn around. That value is c. Of course, if we had a non-continuous function, this would be easy. And it doesn't mean it has to turn around either. It could look something like this, where we have a repeated value here and here, but because of the jump, it never actually turned around. We never had that derivative equal to 0. It also means that, it also doesn't mean that the c has to be centered in the a and b. So we could have a function that is not very symmetric. So if I look at a and b being here and here, well, their center is somewhere around here. We can see where it actually touches 0, where the tangent line is 0, is much closer to a. So it doesn't mean that it has to be symmetric. It just means somewhere between them we have to have that tangent horizontal line. We have to have that derivative is equal to 0. So let's take a look at an example. Let's apply this. Let's use Rolle's theorem to show that f of x is equal to x cubed plus 5 has no extrema. Now hopefully we all know what this looks like anyways, but just kind of being able to come up with a picture in our heads, we want to go a little further. We want to prove this using Rolle's theorem, or really explain it using Rolle's theorem. And when we get to functions that we don't know what they look like, Rolle's theorem really is valuable in helping us determine where our extrema, where will these things hit. So if we think about this function, first it is important to note that it is continuous. The other thing to note is its domain is from negative infinity to infinity. Now I'll have a lot of students stop and say here, well, I thought we could only apply Rolle's theorem to a closed interval. Well, it's true, Rolle's theorem applies directly to a closed interval, but if we were continuous for all values, we could take any subset of those values. We could take any interval within that infinite domain, and we could set that as our closed interval. So again, Rolle's theorem really just cares more about the continuity over the interval. We can always form that closed interval to study, right? In that closed interval, we would drive those ends to the infinities. So what I need to do is I need to determine what do the ends of this thing look like. Well, the ends are going to continue going on forever and ever because the domain is infinite. And then secondly, do we have anywhere in the middle where that derivative is equal to 0? Because those are potentially extreme as well. Remember, extrema can occur at the ends and also at points where the derivative is equal to 0, those turning points. So I need to find the derivative. I take my derivative of my function. It's 3x squared. So if this derivative is ever equal to 0, that is a good place where this thing could be turning around at. Keep in mind, Rolle's theorem does not say that if the derivative is equal to 0 is guaranteed to be that f of a is equal to f of b, right? It's saying if f of a is equal to f of b, then we know that the derivative between somewhere is 0, but the other direction is not true. So we have here a point where the derivative is equal to 0. At x is equal to 0, the derivative is equal to 0. That means around 0, we potentially could have the same values. That is potentially setting up for the for us to have a relative minimum or a relative maximum. So what I want to see next are the values on left and right, are they the same or are they not? And so I have a couple of different ways of looking at this. I'm going to choose to do it with the derivative. I'm going to look at the derivative at, let's say, -1. If I plug in -1, I get 3 times -1 squared, which is 3. Importantly, it's positive. So what we know is as we approach 0, our slope is positive. Let's take the derivative at 1 as well. So we'd have 3 times 1. That's also 3. Now, when we're looking at Rolle's theorem, we're saying, are the functions the same, not are the derivatives the same? What we've just shown is that the derivative is the same on either side of 0. So that tells us that the slopes of f of x from the left of 0 are increasing, as are the slopes. I shouldn't say the slopes, let me say the, how do I want to phrase this? The graph of f of x is increasing from the right, so that the slopes are positive, not that they're increasing, are positive. From the left of 0 positive, as are the slopes from the right. Therefore, f of x is strictly increasing. Except for at x is equal to 0. Let's think about that for a minute. If we're strictly increasing, except for the one point that we see that we have the derivative is equal to 0, if we're strictly increasing, are we ever going to be able to have those same function values? No, we can't. If our graph is strictly going up, the function value would never repeat itself. So f of x can never repeat its y value. That means there will never be an f of a that is equal to an f of b. If these y values are never equal, if we never have this turning point, well then that excludes the ability to ever have a minimum. So what we would say is the function, or I said a minimum, couldn't be a maximum either. The function f of x is equal to x cubed plus 3 is continuous on negative infinity to infinity. We found f prime of x is equal to 0 only at x is equal to 0. Therefore, x is equal to 0 is the only possible extrema internal on the interior of the function. Since f of x is increasing, to both left and right, from both left to right, from left of 0 to right of 0, x is equal to 0 cannot be an extrema. Furthermore, because the function is increasing, it must approach negative infinity as it heads left, and positive infinity, I'll just use a symbol, and positive infinity as it heads right. So we've shown that the endpoints are not extrema because they are infinite, they just keep going. We've also shown the interior doesn't have any sort of extrema because we looked for its derivative, we found where the derivative was equal to 0, and we said that can't possibly be an extrema because of the increasing nature of the function.